Welcome to the first edition of the eBeam Initiative video journal, The Fine Line. I'm Aki Fujimura, CEO of D2S Inc. We are the managing company sponsor of the eBeam Initiative. In these video journals, we like to go through some of the industry or supply chain perspectives, as well as go through some of the technical details of all of these new advances in the eBeam technologies. And we also would like to provide the overall perspective of why eBeam technologies are so important and why eBeam technologies are increasingly difficult and therefore more valuable in the supply chain that's providing the semiconductor technology, continuing on in the Moore's Law. It's really amazing. Moore's Law is an amazing thing. And eBeam technologies are increasingly important in doing that. My background is mostly on the EDA side, and what I notice is that every technology, every kind of a technology, whether it's timing or anything to do with parasitic extraction or anything that's simulation related, first you try not to do anything because the computational power required is tremendous and you like to do things as fast as possible, right? So you try not to have to use anything, and then you go to a rule-based approach because simulation is inherently slower, so you like to be abbreviated in how you handle that, so you try to do a rule-based approach second. And then you go to a more simulation or model-based approach in how you process, because ultimately, Moore's Law takes you there. Moore's Law takes you to the place where what you have to write is small, and not just small, more precise. The more precise part is the harder part. And in anything, it's like that, but in particular, in eBeam processing, it's like that right now. In eBeam processing for one-to-one dimension things like, for example, nano-imprint masks or for direct write, it's already there. It's already been there for a few years. In mask processing, I would say, I would describe today's status to be rule-based, tomorrow's status to be absolutely simulation and model-based. Right? The 20 nanometer technology node is probably more a rule-based world in reality. 14 nanometer technology node, or 16 nanometer technology node, depending on who you are, is going to be absolutely a simulation-based world. It's a normal progression. You would expect that. I think what we're seeing is exactly that. And the benefit of doing this is that mask CD uniformity will be better, and mask write times are better simultaneously, and therefore the kinds of shapes that are available for OPC engineers for the wafer processing side is vastly improved. That is, there are less restrictions on the kinds of shapes that they can use to make the wafer quality better, and that will in turn make the wafer processing better. So this is exactly in line with the kind of advance in overall semiconductor technology to improve along with the Moore's Law, or even go faster than that if we can, and using the eBeam technology in particular to do that. Mask processing in particular, precision cannot be compromised, nor can the processing time required to make the masks. The data preparation time also is incredibly critical because turnaround time is essential between tape out and the first wafer layers being produced. So there's a very, very difficult trade-off between processing time and simulation accuracy that has to be achieved. And one trick that turns out to be incredibly valuable is the use of the supercomputing power that's available from GPGPUs. Most notably in the D2S implementation of NVMDP, we used K10s, Kepler's K10s from NVIDIA, and it's very timely that John Chen is joining us in the eBeam Initiative Advisory Board this time. It's an incredible capability. 400 teraflops is available on a 2-rack standard configuration, and it's scalable up to 4 2-rack systems, or 1600 teraflops. That's really a supercomputer. So it's really amazing that that kind of power of computing can be made available to regular people like me. Right? It's really just could not have imagined it 10 years ago. And the availability of this kind of computational power is allowing us to provide a processing time that's reasonable without compromising any of the accuracy required to do a simulation-based or model-based processing of masks. And this, in turn, is hopefully going to contribute to making wafers that are more reliable and more with enhanced process margin. So to wrap up, this edition of the Fine Line Video Journal from the eBeam Initiative talked about one particular aspect of an interesting development in the application of the eBeam technology for the semiconductor manufacturing and continuing on with Moore's Law. In the future editions of the video journal, we will cover many more aspects. There is multi-beam, there is direct write. There are many ways in which this incredibly fascinating technology using eBeam can contribute to furthering the semiconductor agenda. I'm very excited about eBeam. I really just love this eBeam field, and I look forward to contributing more editions of the Fine Line.